Yep, we are on now. I think we can see ourselves on the thing on the screen share. Um, so yeah, before I hand over to Carlos, maybe I will just, for those of you on YouTube and for those who have subscribed to the newsletters, we have a new course coming up on elliptic curve cryptography. This will be a foundation module for another course that hopefully we plan to do on post-quantum cryptography. Yeah, so as you can see, quantum formalism is trying to branch out, catch up with the thing with what's going on in the thing at the forefront of research in quantum computing and related topics. So this will be a foundation for a post-quantum cryptography course. In particular, we will start with the isogeny-based cryptography. So, to understand what isogenies are, these are like special maps on between elliptic curves. So to understand that, obviously, you need to understand what elliptic curves are. So yeah, so anyone who is interested in post-quantum cryptography, it's highly recommended, especially if you are interested in isogeny-based cryptography, to take this course. And likewise, for those who are interested in stuff like blockchain, all these type of stuff, elliptic curves is the underpinning cryptography for these things. So yeah, so just a quick note there. If you already subscribed to this quantum hardware course, you would have already received a newsletter, an email from me. Initially with the wrong date for the Q&A. I think I put November the 13th. Bob, thankfully, Bob noticed and he got back to me quickly. I think there is a typo. I was like, yes. Yeah, so apologies. So the first session on the elliptic curves course will be December the 13th, and it will be mostly like a Q&A session and to introduce the curriculum in the form that we already shared in the newsletter. There's already more or less the curriculum you can download to see what mathematical topics will be covered. We'll start from very basics. Obviously these things can become very complicated, but if you start with the basic stuff, it helps, to review finite fields, all this stuff before we go up. Okay, so that's it. So Carlos, without further ado, I will hand over to you, and I will be going away now. Yeah. So to the rest of the audience, enjoy your session.
Okay, thanks, Bombardier. Thank you, everyone. Well, today I'm planning to starting the new Shuang book finally, and then I'll show my idea in principle is to show some slides just to give an introduction on the team. I mean, you are not with. I think I still need to. Let me share. So my idea is to show some slides in the beginning, and then I'll show an example where I will use like the whiteboard. Okay. So this is here our course, quantum hardware, optical models. This is the first class. I mean, where I'm using the new Shuang book. And basically, the things I'll talk here, mainly in the slides, are that it's a summary from the chapter 7, the new Shuang book. And then in the calculations, I'll give more details than it has in the book. So let's start. So we start with the basic questions. So the question is, what are the experimental requirements for building a quantum computer? So this is the summary. So the elementary units of the theory to have a quantum computing are the quantum bits or qubits. We always call qubits. So qubits are just like two-level quantum systems. And today I'll show one example that, well, using like quantum mechanics is a theoretical example that we could like related two-level quantum systems that it could represent a qubit in this example. So in my first lecture, I think about, I don't know, 2 months ago maybe, we use it was in the lecture that I was showing like the overview from the course. So we use one example related to the spin of the electron to justify like the existence of qubits in nature. That's related with the Stern-Gerlach experiment. So to realize a quantum computer, we must not only give qubits a physical representation in which they retain the quantum properties, but also it's needed to select a system in which they can be made to involve as desired. Furthermore, we must be able to prepare qubits in some specific set of initial states and measure the final output state of the system. So the main challenge, of course, is the experimental. In theory, all of these things seems to be nice and simple, but the main challenge is experimental realization of these requirements are, in general, only partially met. It's not a simple thing because things like noisy can give like the coherence in the system. So first example here is that a quantum computer needs to be one example of these difficulties is that a quantum computer must be well isolated to retain its quantum properties, but at the same time the qubits have to be accessible. Yeah, because it cannot be too isolated that you can have access to the qubit. So this is one of the difficulties. Okay, so in this first lecture, I think I'll use. I'm listening.
Bob, can you mute, please? Got an echo.
Yeah. In this first lecture, we will briefly discuss the 4 basic requirements for quantum computation, and in the end, I will give you one example. Okay, that is a particle in a potential well. The requirements are basically these 4 here. So robustly represent quantum information, perform a universal family of unitary transformation, prepare an initial state, a fiduciary initial state, and measure the output. So okay, so let's discuss a little bit each of this topic, and then we go to example with the whiteboard. So first, representation of quantum information. So quantum computation is based on the transformation of quantum states. And the quantum bits are the 2-level quantum systems and provide convenient labeling for pairs of states and their physical realization. An important detail is that for computation, the crucial realization is that the set of accessible states should be finite. Remember that we in quantum mechanics, when we are discussing the math, the mathematical tools, we can have like working in infinite Hilbert space. But of course, for computation, is something finite. So in case of quantum computation, we in general will use it like especially for the experimental realization, finite number of states is required. So in fact, it's also desirable to have some aspect of symmetry that dictates the finiteness of the state space in order to minimize the coherence. So one example is the spin one-half particle. And this type of particle lives in, like, for example, like on an electron. It lives in a Hilbert space that's spanned by up and down states. And the spin cannot be anything outside this two-dimensional space. And thus, it's a nearly ideal qubit when well isolated. One example was in the Stern-Gerlach experiment, right? As we discussed in the first lecture. But we'll see with more detail in other classes. So, the second topic is the performance of unitary transformations. So, closed quantum systems evolve unitarily by the Hamiltonians. And depending of the system we are treating, we'll have like different Hamiltonians. And to perform quantum computation in a real system, we must be able to control the Hamiltonian to effect an arbitrary selection from a universal family of unitary transformations. One example is the gates that we know that people use to work in the quantum computation, like the Pauli X, Y, and Z gates, rotation gates that would be R, X, Y, or Z. And H here is the Hadamard gate. In this course, we are using the letter H for Hadamard gates and for Hamiltonian in general, okay? So when I'm using one or the other, I will tell you, because I'm trying to follow the notation, the Nielsen-Schwann notation, and then he used the same letters for Hamiltonian and the Hadamard gates. In these gates are gates for single operations, and we also have like C0 gates for more than one qubit. And we have more Toffoli gates and so on. In Toffoli is for 3. Thus, realization of this kind of quantum logic gates is a natural goal for experimental quantum computing. So in this course, not today, but in this course, we'll see some tools that we can use, like to represent these gates. So the control parameters in the Hamiltonian are approximately classical controls. And in reality, the controlling system is just another quantum system. And the Hamiltonian should include the back action of the control system upon the quantum computing. One example that we see during this course is the calling like the Jayne-Cummins type atom-atom interaction Hamiltonian. This will be in the last part of the course. Okay, so today I'll give just a simple example. The next class we'll talk about the harmonic oscillator, and I think the other class we will talk about some optical models, but not this. This is just in the end, probably only next year. This Jayne-Cummins example. So the idea here is, after interacting with a qubit, a photon can carry away information about the state of the qubit, and this is thus this can like invoke a decoherence process. Okay, this we talk about unitary transformations and initial states. One of the most important requirements for being able to perform a useful computation is to be able to prepare the desired input. So the input state preparation is a significant problem for most physical systems. This is being the second part of the course that we'll see ion traps And just here is just one example to illustrate these comments. And ions can be prepared in a good input state by cooling them into the ground state, which is not a easy thing. It's always like a challenging thing because we are treating at very low temperatures. In one example, that will be, I think, in the third part of the course, will be the nuclear magnetic resonance models, where each molecule can be thought as a single quantum computer. Although qubits can remain in arbitrary superposition states for relatively long times, it's difficult to put all of the qubits in all the molecules into the same state, because the energy difference from the molecules, h bar omega, from the state 0 and 1, is in general much smaller than kb t. Kb here is just the Boltzmann constant, and T is the temperature. This is a kind of thermal, it's come from thermal energy from the system. So the difficulty here is that this energy for the quantum system in general is much smaller than the temperature in the medium, and the energy associated to the temperature in the medium. So measurement of the output. So what measurement capability is required for quantum computation? Let's initially think of measurement as a process of coupling one or more qubits to a classical system. You have to have qubits, but they need a classical system to measure. After some time, the state of the qubits is indicated by the state of the classical system. So one example is a qubit state could be represented in this way. And we show, in the example I'll show today, we see that we can represent like the energy levels of the systems in this way, using a qubit in a state similar like this, which each 0 and 1 here is represented by the ground state, is the 0, and the excited state of the two-level atom. And it might be measured. So if after the measurement the detector indicates like the excited state, let's say 1, so the psi, the cat psi, will collapse to 1 with probability modulus square b square. Modulus square of b, probability modulus square of b. Yeah. So this is I think we call this like the fifth postulate, I think. So many difficulties with measurement can be imagined, like inefficient photon counters and thermal noise. And furthermore, during the measurement process, it's required that the coupling between the quantum and classical system be large and switchable, since measurements should not occur when not desired, otherwise they can be a decoherence process. So this is just a summary from the first part of the chapter 7 from Nielsen Schwenk book. I think now we should see one example. The example from a particle in a square well potential, and how to relate this with qubits. So we'll see this, it will be much better. We see this in whiteboard, in the whiteboard. So you guys have some questions now? Just a summary I did, just to give an introduction. Questions? So, oh, okay. No?
I didn't see any questions in the chat yet.
Yeah, okay. So, my idea here, I will write here in the whiteboard And in the end, with this whiteboard, I will like generate a PDF and I'll give available for you guys, okay? And I will do the same as I know that I still didn't send the other PDFs. It's my fault. I forgot like to correct some typos, but I will do this in this weekend. And so I think the last two lectures I didn't give the PDF about the postulates, and I will give the last two and today PDF. Okay. So okay, so the idea is to how I'll try like with this example to maybe to illustrate that four topics, main topics for quantum computation, like how to represent the quantum information. I think there is some questions. No? How to represent quantum information, perform universal family of unitary transformation, prepare the initial states, and measure the results. So I think this example can illustrate a little bit. This is
the question on the chat is from Muhammad Reza. From that previous description, it may be reasonable to draw a direct analogy between the classical setup and bath in thermodynamics. Question.
that related about the energy levels, right? Yes, and the
Yes.
I think the answer.
Why are you calculating it?
Let's see the. On the previous description, it may be reasonable to draw directly an analogy between classical setup and Beth in thermodynamics. Yes, because it's related. The KBT is related with the energy, thermal energy of the system. But this we will see that example was just like to illustrate. But we see in the, I think we'll see that example for nuclear resonance in the fourth part of the course. Okay, but yeah, the answer is yes. So welcome. So let's see. So this example is in the box 7.1 in the New Xinchuan book. Okay. So we'll consider you start consider a particle in a one-dimensional box. And of course, this particle behaves according to the Schrödinger equation. This I think we call the sixth postulate. So when I'll call a particle in a box, you consider, let's say, a Hamiltonian H, which give for the kinetic part. The kinetic part can be written this way. P is the momentum, M is the particle mass plus a potential V of x, where to this case, the particle in the box, so as a simple example, V of x is 0 for x between 0 and L, and V of x is infinity otherwise. Okay? So we have basically something like this. Potential, particle is here between 0 and L. This is x. Okay, here's the potential. So here inside is 0, outside is infinity. Okay. So if we have like the Schrödinger equation, remember the time Schrödinger equation in general is this, we can write in this way, d dt psi equal to h psi, and h psi give us the energy of the system. Okay, and using the Hamiltonian we are considering is this one. So we have p squared 2m plus v of x times psi is equal to this. But v of x inside the box is 0 inside the box. So we have just p squared 2m psi equal to this. Okay, but how to represent p? I mean, I don't know if I have time, but we can like have physical or some math arguments to tell you that p, like the operator p, can be associated with I h bar in one dimension, in this case d dx. We can show this, we have physical arguments to tell this, but we also can show this like using Fourier transforms in the momental representation and the space representation. But to not lose like the sequence, let's consider this now. And in the end, I don't know if I'll have time to show today, but when preparing this PDF, I will put together the things I will show here live. I will make something like an appendix showing that we can represent P, the operator P in this way. Okay. So in this PDF, I will create an appendix that show these things, because I think we will not have time to show. So this is one dimension. In 3 dimension, this will be like the gradient. So it's one dimension. So let me see appendix from this PDF. Okay, I will show the appendix in. I mean, when I give available for you guys, the appendix will be in the end of this whiteboard. So now is more convenient we work because like the first example we are considering. I will give some steps, and I think for now it's more convenient work in the psi wave function representation. In the end, we return to the Dirac notation, okay? So to give this, we can like multiply both sides of this equation by the bra of x, because we are in one dimension. So this is x psi. So I'll have here, I will use this notation here. So h bar minus 2m. This is I think in the math tools we saw that this is the psi of x. So this is ddx where psi of x e psi of x. Okay. So okay. So let's do this a little bit quicker. We can do this like d squared dx squared psi of x is the same minus 2m h bar squared psi of x, and we can call this, give a name for this guy. Let's call k squared. Okay, so this is minus k squared psi of x. And then we can solve this equation using like, I think this is in the prereq formalities for differential equations, but it's because this is so simple. Let's see, we can like call this. So let's call ddx as an operator. Let's call d. So d square psi minus k square psi. For psi difference of 0, we have d plus minus ik. Okay. So if this is d, so d psi is minus plus minus ik k psi. So d dx psi x plus minus psi of x. And this, we can integrate this. We'll give a log of psi is the same plus minus I k. This is x plus a constant. So psi of x is like the exponential plus minus ik x plus the constant, and it's convenient for us now we write this in terms of cosine and sine. So this will be cosine of k x plus b sine of k x. Okay. So this is my psi of x. A and b are constants that we need to find. So to find these constants, let's find A and B. So we'll use the conditions. That psi, remember we are in a potential, we are in a box this way. This is infinity, and the particle is here inside. So the psi in the order, psi of this is x equal to 0, this is x equal to L. So psi of 0 will be equal to psi of L will be equal to 0. Okay? Because this is here. The particle is limited in this region. So if you use these conditions here in psi, so using these conditions, in the psi solution, we will have psi of 0 is, so this is the solution, A cosine of 0 plus B sine of 0. This should be 0. Okay? So sine of 0 is 0. So we will have, and cosine of 0 is 1. So this implies A equal to 0. This is one condition. The other condition is psi of L. I already know A is equal to 0, so use this B sine KL must be 0. So B equal to 0 is the trivial solution, but we don't want the trivial solution, otherwise psi is 0 everywhere. We use this condition, that sin KL equal to 0. Put B different of 0. Okay? So this guy here to be equal to 0, it means that KL will be something like n pi. So K, in fact, depends of N, where N could be 0, 1, 2, and so. Okay, let's begin together. Okay, so K N is in pi over L. It's important. It's important because if you remember, as we define K, let's see if it's easy. K is this guy here. So K is related with the energy. So K, remember, K is this QME H4. So NPL is equal to this. So energy depends of N H bar. So the energy for the particle in the box will be N squared pi square. This is square. H bar square divided by 2ml. Okay, so energy is quantized, right? So energy is quantized for a particle in a box, a particle of mass m, where L here is the size of the box. Okay, but let's return. Let's use blue. Let's return here. So this is our psi. Psi is psi of n. X is equal to b sine k n x. So now you can use like the normalization condition, and now we can return, is better return to direct notation. So using the normalization condition, so psi which one? So psi of n, we can write this using the closure relation as the integral of the x in one dimension, right? Psi of n x is psi of n. Okay. I don't remember if we saw this in the math tools, but if not, I think one homework is to just to read. I put here page 121 from the coin book. Coin, I think is this download book. Okay, I don't remember if you see. So this is the it's called like the closure relation that I can means this thing here, dx x, x, this is equal to identity. Okay? Is the identity matrix. In one dimension, you can generalize this to 3 dimension. So I did this. So we can use here this is the x. This is the bra. This is the conjugate, psi conjugate, psi n of x conjugate. This is psi n. So this must be 1. And we know psi of n is this. And psi star is the same because the sign will not change, only the beat. So this, and this is, of course, it's inside the box. So this is 0 in here, okay? Because we are inside the box. The other part doesn't matter because the potential is there. So that the psi is no, sorry. So we're using this here, integral dx, this is b squared sine squared x. And this is equal to 1. So we need to find b, solve this integral. So I'll just put here the answer, like b squared. So the integral of sine squared in this limit, the result will be something like this. Kn minus cos KNL sine KNL over 2kp. Okay, this is equal to 1. But we already saw that sine of k and l is 0. So we have b squared, because this is 0, so this guy here goes away with this guy. So b, let's put b. B is this 2 over f. Okay? It's only this guy and this other survives. So now we have psi n of x over il sine kn x. Okay, but this is just the psi of x. The complete solution involves on time, right? So the complete solution requires a time dependent solution. Contribution. So for a time dependent solution, we have just to solve that first equation we put in the beginning. Schrödinger equation dt sine of t. Actually, this will be English will be partial. d dt sine of t. It's a Hamiltonian psi of t, right? which is the energy. In this case, we already know the energy is quantized. So it's a psi n of t. Okay. And to solve this it's again like we just need to integrate this because the energy doesn't depend of time. So we just need to integrate this, and this will give us like psi n of t. We'll have the exponential minus I en t over h. Okay. This is similar to what we did to the space. But here, I just call the constant one because, I mean, what we really need is the total solution. Thus, the solution is the psi and xt. This is right. This is not, because this is just the time dt. So this is the psi of xt. It's psi of n t, psi of n x. Okay. So basically, we did the separation of variables. So this is the t solution. Is this one exponential? And we could do this because the potential is not time dependent. So I have this times psi of x. Let's write this way. So okay, we can like write this in the direct notation. In direct notation. And just note that this is x psi exponential minus e t h bar x psi n. So you could write this just as my psi n of t. Is this ent h bar psi n. Okay. And now we'll write the complete solution. That's a linear combination, right? The possibilities, the n possibilities. Now, the complete solution, which is psi n of t is the sum an psi n of t. In fact, we don't have the n here. Yeah? Because I sum here is the sum of all the n's. So we can see here that these states have a discrete spectrum. Yeah, remember that n is 1, 2, 3, and so on. In particular, suppose that we arrange matters such that only the two lowest energy levels need to be considered. Need to be considered. Now, what we are doing is making the transition from quantum mechanics for quantum computation. Like try to relate this with the qubits. So far, until here, we are in quantum mechanics. This is the solution that we can find like in the usual quantum mechanics course. But now let's do the transition for quantum computing. So we can write this. We can define. So let's define arbitrary wave function of the type. So let's write, change the color again. Psi of t, this psi here, and let's consider only the two lowest energy levels. Okay, so I can write this as A1 psi 1 plus A2 psi 2. So I will use the notation from Nielsen Schwang. Let's write in the same way he puts in the book. So let's use the Nielsen Schwang notation that he basically call A1 from A and A2 from B. Okay. So just to have the same notation. It doesn't change the names. B psi 2. And this psi here is psi of t, right? This is psi of t. I have a t here. Psi of t, psi of t. So we can use psi of t that we found. The only difference, the exponential will appear. Minus I, E, because it's En, so it will be E1, because I'm using psi n equal to 1, T, H bar, psi 1, plus B exponential minus I, E, 2, T, H bar, psi 2. So we can like simplify this if let's simplify this expression, putting this guy in evidence. E1 plus E2 T over H bar, 2 H bar, is 2 here. H bar. To put this in evidence, we can write this right side here in this way. Psi of t is equal to exponential minus E1 plus Z2 T to H bar A exponential minus E omega T over 2 plus B exponential I omega T over 2. But this omega, I forget here, the psi 1 and psi 2, where omega is E1 minus E2 over H bar. Okay. So we could also do like make psi 1 is the lowest level, let's say it's the ground state, 0, and psi 2 is a excited state, 1. Okay. So we could write this psi of t as exponential minus e u1 plus e2 t to h bar times a exponential minus e omega t over 2, 0, plus b exponential plus I omega 2, omega t over 2, 1. And we could represent like 0 and 1. We could represent this in terms of the matrix row. We could write this as, let's say, exponential minus e u1 plus e2 t over 2 h bar. In terms of a matrix A, exponential minus b over b t over 2. And we could just call all of these things. Let's make it simple. Let's call A bar, B bar. Okay? Where A bar is this first line, B bar is this second line. So we could represent this state psi as a two-level system. So this is two-level system that represents a QB. Now the thing is, one question is, does how two-level system transform like a qubit? So, I think gray is not good. To perform operations to this qubit will perturb H, the Hamiltonian. The Hamiltonian. So this perturbation will be simple. It will be something this way. So consider the effect of adding the term. So we'll perturb the potential in the Hamiltonian by one delta V of x, V0 of t, 9p squared over L, x over L minus 1/2. This value choose because in the end the answer will be simple. So we understand why this is constant here. He chooses like because in the end the answer will be only in terms of V0. So we can see this, like how to represent this. We can look in the basis of a two-level system. This can be written by taking the following matrix elements. So we could like define Vn M as the matrix of psi n delta E of x psi n. And we can use again the closure relation to have this integral of x prime psi n x prime delta V of x psi. Double integral because I define psi x and I define x prime and x. Okay, so this delta V, I can bring here to here because it doesn't act in the x prime. So this just dx prime delta V x Psi x psi. And this guy here is just a delta of zero. I also don't remember if we discussed this in the math tools, but again, you can see the same pages 131. So delta x prime and delta of Dirk. It gives the page 121, the coin book. Okay. And it has this property. Psi of r integral dr psi r prime r. Okay. So if you use this property here, one of the integral goes away, let's say x prime, and we have e and m integral dx delta vx. So this guy go away using this property. So we have psi n of x, not x prime, because the prime becomes x psi. And this is the same delta vx psi n x psi n x and m. You know? This is m. This. So we can use again. This is the general. So for n equal to m, if we want to find the components of this matrix, so let's see the diagonal first. N equal to m. So we have v and n. This will be simple integral inside the box, so 0 to L dx. And I'll just use the delta v that we define. Is this 9p squared 16L x over L minus 1/2. And the psi that we found, that's just the sin square kn x. Okay, this L here comes from the side. Okay, so we just need like to solve this integral now. Solving this integral, we can like write because see here we will have integral of these two types. But here this way. Go faster. We have types of integrals. This x sine square and the other is just the sine square. Okay, if we solve these integrals and put here, we'll find that v and n will be simple. The contribution from the first is times a constant that called is like c of t will be c of t, but this is constant, right? Doesn't depend of x. We'll have this first integral will contribute to L over 4, and the second minus L over 4. Okay. This, of course, in this range, 0 to L. So this will be 0. This will be 0. And then right. And for n different of m, v12, for instance, we'll have psi 1 delta vx, psi 2, and v21 is the bra of psi 2 delta v, the cap psi 1. We can show that these both will be the same integral 0 of L dx is squared 2 over L in k1x delta vx, and here 2 over L sin k2x. Okay, this guy is here. And this is the same because, I mean, it commutes, right? The sign could be the first or the second, because the bra of the sign is the same of the cat, the sign function. So we need to calculate only one, v12. That again will be a constant. I think it's the same constant, c of t, integral 0 to L dx, and this function x over L minus 1/2, and the sine k1 sine k2 of x. So we can solve this integral. This the angle of the sine is not the same anymore because we are out of diagonal terms. But we can solve this integral, and we will find that v12 is just the v0 of t. V0 is inside this c, okay? And just I think it's better not put the c, put everything, every space. V0, 9p squared, 16 to L. Okay, it's the constant outside. So solving these two integrals here, one depend of x and these two signs, and the other only the two signs, we'll find this. Okay, these integrals are as homework. That's simple. And this is the same of V to 1, because it doesn't matter. It commutes the sign. So we can write this perturbation such that to lowest order in V0 the perturbation of H is, I'll call H1. That can be written as V0 of t. In terms of the diagonal components are 0, we calculate, and the out of diagonals components are just the V0. I put V0 here. This perturbation works like a X gate, Pauli X gate. Where is the Pauli X gate? Okay, just to conclude, almost. So this perturbation generates rotations around X axis. And similar techniques can be used for single bit operations. By manipulating the potential function. So the same, this example, these are rotations around X, but we can like have other examples to have other type of operations. So operations by manipulating the potential. So we just, let's say, we just show how a single qubit can be represented by the two lowest levels in a square. Well, potential. And how perturbations perturbations of the potential can affect computational operations on the qubit. Okay, this is the positive things. But in fact, this is just a very simple theoretical model. So we can say, like, let's see the negative things. However, perturbations also introduce higher order effects. Not only 0, 1, it could be 0, 1, 2, 3, and so on. So we could lose our qubit representation, right? So we could have like perturbations introduce high order effects. So other levels would enter in this picture. And our two-level system begins to fail. Other point, negative point, is in real physical systems, boxes are not infinite. And because of that, some transitions are not infinite. Thus, transitions from the bound states to the continuum of unbound states would be possible. All these problems all these, let's say, issues lead to the coherence. Since it could destroy the superposition states. That's 0, 1 state for our psi. So okay, I think this is like enough for today. What you guys have some questions? Like in this was like the first lecture, my lecture that I use like a lot the whiteboard. So also I would like to know your guys' opinion. But my intention is to like in the other lectures like continue this way because we have not used his phone is maybe because all this calculation he just doesn't show. He just like consider that the reader know had did these calculations before. So that's why I'm trying like to give more details in the calculations. So, but I mean, you guys know if you guys know, but I don't know. We don't have we have like 4 people here live. Maybe the guys in internet in YouTube. I don't know the familiarity of with the math, the quantum mechanics math people has. So okay,
I
okay.
think it's easier to follow, yes, if you are using the whiteboard. It's easier
The
to
whiteboard
follow.
is better. Huh? Yeah,
Huh?
yeah, I think because I mean today the calculation is simple, but it be like when you consider more real systems, will be more a little bit more complicated as well.
Then the whiteboard will just help, yeah, us at least.
Yeah, yeah, yeah. Because I mean, only the slides will be will be harder to follow, I think. And I want to do more than what what the New Sinchron books have. So
As I know, at the U.S. universities, they are still using the whiteboard, so they do not use the ready materials, but instead they are using, they are presenting the material exactly the way as you today.
yeah,
Yes, so it's very looks like proven to work. Yeah. So I think it's very good idea, and personally I like it. I don't know
yeah.
what about others.
And I will generate the PDF with this whiteboard and send to you guys. I'll do this weekend.
I very appreciate it.
Yeah, thank you, Carlos.
Okay, thanks, George.
Yeah, I find it helpful to see the development in real time on the whiteboard.
Yeah, I think it's better. And yeah, again, I will provide the like the appendix with the justifying like the P because we not have time. I mean, it's more than 1.5 hours. So I think I should stop. I will stop recording. Otherwise, Bumble the video will be too long. So, okay, so I'll stop recording now. Okay, thanks guys. Thank you people from YouTube.
Thank you very much. Have a nice weekend.